And okay. So today we are going to finish up A1. Okay. So we went through lots of basic stuff in Unit A1, and then we talked about wind tunnel testing and the pressure distribution over the surface, airfoil, and then today we are going to take a look at the boundary layer. So this is just the basics of boundary layer today, and then we are going to finish up A1, then get right into A2. Okay. All right. Good. So before we even begin today, let's just take a look at the updates. There are a few updates since last week, Thursday. Today is a Tuesday, isn't it? Okay. So since last week, Thursday, what are the updates? Of course, you're working on take-home quiz 2, which is due. Already due. Did you turn in? Did you turn in? Okay, I hope so. Oh, that's due today. Yeah. So, I hope you turned in. Quiz 2. Okay, good. This was an easy one. In other words, this is a very basic mechanism of how the panel method actually computes the drift coefficient for a given cross section. Since you guys start using the software Xfoil/Xflyer5, actually you don't use Xfoil. Xflyer5 uses Xfoil as a core component, as a batch processing. But take a look at Xfoil actually helps you to get started. This is how this software works, panel method. So panel method computes the pressure distribution over the surface of each panel, and then you're going to integrate numerically to determine lift coefficient. So I hope you did this, and I hope you understood how this panel method works. Okay. So this is easy deal. It's just a numerical integration of surface pressure distribution to get lift coefficient. Of course, you should know, right, from Edo. There's one student who's not taking Edo, so I can't really say that, but I hope he catches up. Jordan, right? Is Jordan here today? No. Is Jordan online? No. What's going on? I hope we are still in class. Otherwise, Dr. Ashworth is going to kill me. Oh, you wrote good student. Okay. Well, I hope you can get too bad. But anyways, okay. I hope he's still with us. Is he? Is he? I mean, who's the teammate?
Is he alive?
Okay. Well, I hope so. Take care of your teammate, okay? Please, whoever it is. Who's Jordan's teammate? Well, you guys stay quiet.
No one knows.
Okay. Anyway, so Q2. This is a fairly easy deal. Okay. And then also Sunday, I made an announcement. The course project team formation for the phase 1A, which is very first phase of the semester project, will be closed by the end of today's class. Oh yeah, today. If you fail to sign up for a team, you cannot participate in phase 1A of the course project. As you form your own team, please read the phase 1A document. Document is now active. Here, you go to course materials page. Start working together. Each team should receive 2 shared OneDrive file folders. One is for submission, one is for graded work, just like similar to your homework assignments for the project phase 1A. Okay, and then I'm going to announce the due dates soon. Let's just double check everybody is signed up for the team or not. Okay. Like this. All right, so let me just check Danny. Yeah. Okay. Also, so you go to Ernie, Canvas. And this is Flight Mac. and people post project. Okay. Oh, looks like everybody signed up. So this is team 1, team 2, huh? Oh, so you trust your teammate. So suppose if your partner drops you all by yourself, team 3 2. I hope you guys trust it. Well, team 4 2. Lots of 2-person teams. Do you trust that much, your friend? Wait a minute, I don't see Jordan's name, so he dropped it. No, he's here. Okay, Cody. Okay, Cody. You better communicate with Jordan. He's not online either. Who's Cody? Okay, that Jordan is your partner. Okay. All right, so everybody's got your own team. Good, great. So I'm going to send you to OneDrive file folder. Okay, today. Good. You can still change around before this class ends. You can change around if you want to. You can dump your partner, join into this two-person team, make it 3. You can do that, no problem if you want to. Okay. Okay, so that's it. Do you have any question so far? Doing okay? So what is the project? Phase 1A. Let's take a look. Okay. So this is the documentation for project phase 1A. Okay. So this phase is all about, okay, let's get to know your software to begin with. That's it. Nothing much. So you're going to be given lots of information here about the two software packages. One is Xfoil, the other one is Xprior 5. The software you use will be Xprior 5. Xfoil is a core component of Xprior 5 anyways, developed by same person. Okay, so you're going to start with Xfoil. Xfoil is a panel method. Panel method is covered in Aerodynamics 1, which is Unit D3. So if you want to know a little bit more about basics about panel method, start with Aerodynamics Note D3, which is already given here. This is Note D3, okay? And then this is the home page of Xfoil, and this is a YouTube channel of the science of flight, and there's a person who actually spent tons of time in Xfoil and then providing a tremendous amount of a self-guided tutorial homepage of YouTube. So you can go through it. I think I would even recommend you trying to download and run Xfoil based on this self-guided tutorial. It doesn't hurt you because Xfoil is basically, it's a single software to simulate single cross-section. That's it. So if you want to create this kind of cross-section of a wing, you want to analyze it, you can use Xfoil to analyze it. Okay. And next one is Xprior 5, again, home page, and also, what's that? Yeah, this is home page of that. And the next one is that you visit Aerodynamics 1, Unit D3 notes, Xprior 5, Aerodynamics Analysis Tool. So this notes provide you 3 very basic examples of how to use Xprior 5, simulate 2D cross-section first to build a database, and using that database to design wing and then simulate the wing to come up with the wing performance. Okay, very basic examples. Okay, so you are going to go through it. Okay, and then you are going to create a report. Report template is already given. You can download the report template right here. This is a Word document. Okay, so open it. It just looks like this. So I want this much details, and then you just fit in. Okay, so each member of your team actually take a part, fit in the information. Now, as you do Xfoil, because Xfoil is actually not the software you use. Xfoil is the basis of Xprior 5. So I don't need that much detail here. You just summarize what it is and try to understand and share the information with the rest of the team. Xprior 5, as you actually run it, I would actually recommend you take a screenshot and cut and paste and drag it into this document so that each team member can actually use this document to actually run it. Otherwise, you're creating like just a document just to be document like a BS. No one uses kind of document. All right, that's a waste of time. So please make sure you develop a very nice, useful, document at least for your team. Okay, as you try to run this example, take a screenshot and cut and paste the screenshot and put some short explanation so that your other teammate can actually look at it and run it. Okay. Now, Xprior 5 is open source, and then they just keep releasing new releases all the time. So the document of Unit D3 notes is probably obsolete. So graphic user interface may look different. It's not my fault. It's your responsibility to keep it up those things. So it looks slightly different from old versions. You need to make sure capture that. Okay, screen capture, cut and paste, and then explain so that you can use that documentation, which is refreshed and up to date, and shared within your teammates. Otherwise, this project is like totally meaningless. Phase 1A. Okay, so phase 1A, make sure you do a good job creating a fairly useful document to be shared. Okay, especially Xprior 5 portion here. So brief history, and here basic 2D budget analysis. Okay, so this one could be fairly lengthy, this one. In other words, you're going to try to run homework. You're trying to run Note D3 of AR1, but AR1 is very obsolete. Sorry for that, it's old version software. So new version software looks different. In other words, you need to catch up those things right here, and also right here. Okay? If you do poor job, you're gonna suffer later. It's your decision. If you do a good job now, and then the rest of the semester goes very smooth, or you do a crappy job here, the rest of the semester, your entire team suffers through either way. You make your own decision as an engineer, okay? Either way is fine for me. Any question here? Okay. So again, so those two are quite important. Xprior 5, 2, basic 2D airfoil batch analysis, 3D wing design and analysis. Okay. So I would expect you're going to renew and refresh Unit D3 notes of aerodynamics 1. Okay. If your team do an awesome job, that notes might be recycled to be Air 1 notes, later in the future. I don't know. Congratulations if so. Okay. Any question? All right, good. Okay. Now, SAE group, you don't need any of those. You just do whatever you need to be doing. Okay. Okay. You are running under the completely different standard. By the way, I tried to recruit one person from Air 1.
Yes.
Okay, you can grab that person and put it under your wing. Let her do everything, well, something like that. She is doing everything perfect right now, 100% in my aero class. Amazing. Class average like low 50s right now. And this person is 100%. Okay, she does everything perfect. So let's grab her. Okay, she's SAE member. That's it. She's a transfer student. She doesn't know what the heck about it. Okay. Any question? Anybody? All right. So let's just keep going today. Okay. Unit A1, boundary layer. Okay. So of course we don't have to sort of cover what is boundary layer. You guys know that. In other words, if we include viscosity, of course, boundary layer need to be analyzed. Boundary layer development is usually independent from the solver. In other words, Xprior 5 is a panel method code. Panel method is usually based on the ideal flow study. In other words, boundary layer is completely ignored usually, right? However, can you do such a thing? No. We want to include, okay, boundary layer development over the surface. Especially, I'm interested in transition point, from laminar to turbulent transition point. Okay. So when you do a CP plot in Xprior 5, if you turn on viscosity, it is going to actually show you the transition point from laminar to turbulent and also separation point. And once the flow separates from the surface of the panel, you cannot compute anything, right? So that's when the software starts saying, I cannot converge, I cannot converge, I cannot converge, no data, no data, no data. Then you wonder about, hey, what's going on? This software doesn't compute anything for me. That's the location where you have a flow separation from the surface. Once the flow is separated, panel method cannot compute anything, of course. All right. So panel needs to rely on the surface that is still stay attached. As long as the flow is attached, of course, it is going to create the skin friction drag. So you have to keep that into account. Skin friction drag coefficient now come into play if you turn on the viscosity. Now, of course, transition needs to be predicted from laminar to turbulent. Once the transition happens, of course, the thickness and the character of the boundary layer model changes. We have two different models. One is a laminar boundary layer model. The other one is a turbulent boundary layer model. Depending on the type of the flow, you have to switch the model. We're going to talk a little bit more detail about that in Unit A2. Okay? Flat plate boundary layer model. Okay. So this is a boundary layer developed on a flat plate. Okay. Flat plate means there is no pressure gradient. Shape is flat. You can actually simulate a non-zero pressure gradient surface, such as you design your cross-section of a wing called airfoil. It comes with certain shape on top surface and bottom surface. That is not the flat plate. Of course, that shape can be built into account for the model. But every model of boundary layer starts from flat plate model. Okay? Anyways. So velocity is 0 on the surface. This is a non-slip condition, of course, coming from fluid mechanics. And velocity gradually increase and increase and increase, hit edge velocity. This is the edge of the boundary layer. So boundary layer thickness can be defined, okay, where the location that the velocity becomes edge velocity, that's the edge of the boundary layer. But boundary layer thickness is given here. So typically, okay, so this is the supersonic fighter aircraft wing flowing through this air. Flow velocity is about 500 meters per second. What is the boundary layer thickness? A few millimeters. Very thin layer, obviously. Glider wing with 1 meter chord length, of course, flowing through this air, flow velocity about 20 meters per second. Again, a few centimeters. Much thicker, but still very thin, like this thick over the surface, okay? Now, if you're talking about ship of water, flow velocity 10 meters per second-ish, boundary layers as thick as 1 meter, okay? Well, you can sort of visualize it. If the ship is moving very slowly in a very dirty ocean, you can see the boundary layer, of course. You can visualize it. Smooth ocean and land, air wind of the land, flow velocity 10 meters per second, boundary layer thickness is as thick as 100 meters thick. In other words, if the car is placed in the wind tunnel, turn on the wind coming in, okay, boundary layer is formed up from the ground. So the car is actually sitting inside of the boundary layer. What are you testing for is the situation. So ground vehicle wind tunnel testing is not easy because usually people need to suck the boundary layer out. Otherwise, you're testing everything inside of boundary layer. Okay, nothing makes sense. And then car is not moving. You have to move the car. Well, that means I have to put the conveyor belt on the ground and turn it on. The car is moving. Boundary layer is sucked up, and ground vehicle wind tunnel testing is not easy. Okay, it's one of the most difficult wind tunnel testing setup. Anyways, okay. So this is a boundary layer transition. Transition from laminar to turbulent happens always. It depends on the shape, of course. It depends on the Reynolds number, of course. Depends on so many things, but you can predict it nowadays. Okay. Now, also after the transition, typically happens is a boundary layer separation. Boundary layer separates when the surface skin friction coefficient becomes 0. So flow separation is associated with the 0 skin friction drag coefficient. Now at that moment, flow is separated, the different type of drag starts to kick in. What is it? Drag due to flow separation or pressure drag. So always we have a trade-off of two things. Viscous drag, you have two things. One is if the flow is attached on the surface, skin friction drag coefficient. The other one, once the flow separates from the surface, pressure drag due to flow separation. Those two trade off, okay? Those two added together is called profile drag. How's that? Do you remember those from aerodynamics? Anybody? I mean, I covered it. Didn't I cover it? Didn't? Oh, wait a minute. What is that response? No, I didn't.
remember that, sir.
Okay. So flow type, laminar versus turbulent. Okay. Obviously, the flow is laminar. It has a very nice velocity distribution, and then slope here. This slope is a slope of a change in velocity, dB dy, slope taken at y equal to 0. This is called boundary layer velocity profile. Multiplied by this slope times viscosity mu gives you tau. This is a tau wall shear stress. Okay. Turbulent flow is much more flat and fat, and change happens very quickly, very nearby surface. So the slope is much larger slope. Multiplied by viscosity gives you much larger skin friction drag coefficient. So the reason why turbulent flow comes with higher skin friction coefficient is because the velocity profile slope is larger on the surface. Okay, so wall shear stress of turbulent flow is much higher than laminar flow. The reason is, of course, velocity profile change slope is much higher. Okay, at the wall. Anyways, those are some basics of boundary layer. Have you ever seen boundary layer with your eyes? With your own eyes, have you ever seen boundary layer? Let's just take a look today. Okay, I have a video. Okay, so this is the video I took long time ago when I was a graduate student trying to graduate. Okay, so this is a boundary layer flow visualization. This is the water coming in from right to left. So this is the water flowing. Okay. So this is the solid surface. This is the solid surface. Water is incoming. Velocity on the solid surface is 0. As you move away from the solid surface, velocity gradually changes and hit the edge velocity. So you can sort of tell the boundary layer thickness of this case. This is laminar boundary layer. This wire is a platinum wire, which is probably thinner than your hair. Very expensive wire. Then you are going to apply 200 volts of electricity. Very thin wire, high voltage in the water, actually making water splits into hydrogen and oxygen, and then hydrogen becomes a small tiny bubble called hydrogen bubble. Hydrogen bubble is so small, it's almost neutral buoyant with the water. You can visualize. This is called hydrogen bubble flow field visualization of water. Let's take a look. Here we go. So those are hydrogen bubbles created by this platinum wire. Look at that. This is velocity 0. Velocity gradually changes, hit like a uniform flow. So this is boundary layer thickness of laminar flow. Okay, I can actually pause this 200 volt voltage to visualize the boundary layer. So now you are seeing boundary layer with your own eyes. So thickness-wise, this is probably, I don't know, about 2 centimeter thickness. You are really zoomed in using high-speed CCD camera. Okay. Obviously, this is the boundary layer developed on the surface, flat surface. Okay. All right, so this is the wall shear stress. Again, dB dy, this is the velocity profile multiplied by, this is dynamic viscosity, is going to get you wall shear stress. Now, wall shear stress leads you into the skin friction drag coefficient. Okay. When you define a skin friction drag coefficient of your airplane, obviously your airplane surface is quite important. How much surface is exposed to the external air is a big thing. Okay. So you are going to count every exposed surface, something called wetted area of the body. If you pick up your airplane design, dip it in the water, how much surface is wet. That's called wetted surface area. So every surface is going to contribute to the skin friction drag coefficient. Okay? So this is called skin friction drag coefficient. You're going to figure it out when you design airplane. This is going to contribute to your drag. Okay? Profile drag coefficient. Part of it is a skin friction. Part of it is a pressure drag. Okay? And of course, Reynolds number is defined based on certain lengths x. Typically, if you're talking about cross-section of a wing, this x is a chord length. If it's a wing, it's still chord length, yeah, I guess. Because, yeah, this is a Reynolds number. Reynolds number is going to be used to predict the transition. Something called transition Reynolds number, which is quite important parameter when you run X prior 5. In other words, you can define transition Reynolds number all by yourself, or you can force transition at the certain chord lengths, or you avoid the transition at all. You can control those things, right? Okay. Well, you're going to run those things. Do you know? You used it, right? Of course. Transition Reynolds number, yes, you can control that. That's a critical value, usually 9 or something like that. You can change it, or you can actually put the tripwire here, force transition at this point, or I can avoid the transition at all. Okay, we're going to discover those things in X prior 5, I hope. Okay. So anyways, let's take a look at okay. So let's take a look at example 3.6, this page. Okay. An airfoil in a wind tunnel test section has a critical Reynolds number of 6 times 10 to 5. Critical Reynolds number means that once the Reynolds number hits this value, you're going to expect the transition from laminar to turbulent flow. Okay? If the wind tunnel is operating in standard sea level atmospheric condition with a test section velocity magnitude of 90 meters per second, how far aft of the airfoil's leading edge will boundary layer transition laminar to turbulent occur? So based on the critical Reynolds number, let's just predict the transition point. Okay, this is easy. I mean, if you are given this kind of information, yeah, great, but usually not. So Reynolds number is, as it's defined, goes rho times velocity b times x over viscosity mu. So let's just change this equation into x, something called x transition is equal to whatever the Reynolds number critical Reynolds number multiplied by viscosity mu divided by rho times velocity v. Okay. So let's just plug in and find out. Critical Reynolds number is given 6 times 10 to 5, 600,000. Reynolds number, critical value. Viscosity of air at the standard sea level is, I give you 0.0000, 0.00001789. Unit is weird, kilogram over meter sec. Dynamic viscosity of air at the standard sea level. Standard sea level air density, I know that, 1.225 kilogram cubic meters. Velocities happen to be 90 meters per second and wind tunnel. What is transition point? Please compute. People on line 2, give me value. What's the value? People online, are you computing? Are you computing? Oh, they're so quiet now. What's the value? Wait, are you? Go ahead, Matthew.
0.09836.
0.09.
9736.
9736. What's the unit? Meters. Any confirmation?
Yes. Yeah.
Okay, good. So this is a transition point. Okay. So measured from leading edge, this is 97 centimeter, yeah? About 97.36 centimeter, you are going to have a transition from laminar to turbulent. This is called transition point. So you're going to expect the laminar to turbulent transition of boundary layer at this location if the critical value of Reynolds number is given 600,000. Okay? So this is exactly how your software handles and treats your viscosity if you turn it on. Okay? If you turn it off, of course, you're going to completely ignore those kind of things. So in other words, there's no skin friction drag component into your drag coefficient. You're going to compute on the drag due to flow separation. Okay. All right. That is essentially Euler solution, right? If you turn it off, boundary layer model, you are solving Euler's equation, Euler solver. So software X-Flyer 5 is a panel method. Panel method is ideal flow, and then if you add on ideal flow plus boundary layer, that is Euler plus boundary layer solution. As long as flow state attached, you can analyze your airplane. Okay, that's called panel method X-Flyer 5/X-Foil. Okay. Any question here? That's it for Unit A1. Let's move right into Unit A2. Okay. All right. So now we are done Unit A1. That means homework must be due sometime. I'm going to announce it. Okay. So homework A1 is due somewhere soon, sometime soon. I'm going to announce it too. Okay. Unit A2 is something called airfoil characteristics. So we are going to take a look at a little bit more in-depth talk about two-dimensional aerodynamics. This is essentially the view of Air1, sort of. So we are going to talk about airfoil shape, symmetric versus cambered airfoil. Of course, you know that. And then let's just take a look at some basics of pitching moment, Reynolds number effects, lift and drag coefficients, NACA airfoil data chart, 4-digit, 5-digit, and 6 series, stuff like that. And then we already talked about airspeed conversion ICE-T, okay? But ICE-T we talked about was based on the Bernoulli's equation, which is less than 0.3 Mach number. So suppose if your airspeed is more than 0.3, in other words, density change effects comes into play. How can we modify that equation? Do you remember those equations, by the way? You know, more than 0.3 Mach number airplane airspeed equation from Aero 1. Do you remember that? I'm kind of curious. Or you have no clue? Wait a second. Wait a second. You should keep me happy. Otherwise, suppose if I turn into bad mood, all sorts of bad things start happening. Like Aero 1 class, because Aero 1 class, nobody remembers anything about fluid mechanics. I get mad, and every class I'm kind of getting bad mood. Anyways, let's take a look. Which unit? I talked about airspeed. Aero 1. Unit A, right? Unit A4, right?
Good question.
Unit A4 airspeed measurements. Do you remember that? For those who took my aero class, I know who took my aero class. Particularly like well, actually 4 people took my class. Anyway, let's take a look at Unit A4. Lots of things. Scroll down, lots of things. Well, you run this much things from arrow, lots of things. Okay, airspeed measurement. What's that? So, measurement of airspeed. This is airspeed equation from Bernoulli's equation. Of course, you know that. But this is only less than 0.3 Mach number. You know that too. So suppose if it's more than 0.3 Mach number, what kind of equation did you get? Do you remember? Don't worry, quiz 3 is going to show up. You have to do it. So do you remember? If you don't remember, Rude Awakening will show up later. Quiz 3, you have to do it anyways. How did you do that? This is based off of Bernoulli's equation, right? But only less than 0.3 Mach number, right? Okay, do you have a better equation which is more than 0.3 Mach? Somebody said energy equation. Yeah, that's right. Here we go. So this is airspeed equation for more than 0.3 Mach number. How did you get this? Instead of Bernoulli's equation, you use different equation. What is it? This is the equation, something called isentropic flow relationship energy equation. Okay? Then picked up that equation, and then you come up with airspeed equation for more than 0.3 Mach number. This is based on, by the way, Bernoulli's equation. Anyways, Bernoulli's equation, compressible subsonic flow version, called energy equation. Okay? So can you derive this equation? I hope so, because it's going to be quiz 3. So I hope you can do it. Okay? So this is compressible subsonic airspeed equation. We are going to take a look at it in Unit A2. Okay? So that's ICE-T, the complete story. Okay? Too bad, you can't escape it. Airfoil compressibility effects. In other words, panel method is based on less than 0.3 Mach number. Density change is not counted. However, if you want to design your airplane, which is capable of flying more than 0.3 Mach number, what would you do? You have to correct compressibility. It's called Prandtl-Glauert correction, compressibility factor correction. We are going to cover that here. Okay? And then we are going to take a look at the complete boundary layer equations, laminar or turbulent flat plate based. You're going to add on that boundary layer results on top of the tunnel method solution, which is combined Euler plus boundary layer solution. That is exactly what the software X-Flyer really gets. Plus, if your airplane is high-speed airplane, you can actually correct compressibility, Prandtl-Glauert. So 3 things hovering around right now is core solver, which is panel method. Okay. If you want to add a boundary layer model, you're going to turn on the BISCLASS model, and then boundary layer model is added on. If your airplane is more than 0.3 Mach, turn on Prandtl-Glauert correction, just add on. That is your solver X-Flyer 5. Okay. Anyways, let's get going. Okay. All right. So let's just start with a very basic fundamental idea of airfoil shape. Of course, airfoil shape needs to be described. Okay, it's called nomenclature. You know that. So this is the cross section of a wing called airfoil. Airfoil is essentially this kind of thing. So you are given cross section of a wing, a unique cross section called airfoil, and then you are going to create a wing which is basically wingspan is 1. This is called unit span. Okay. That is called airfoil. So when you do a testing of a 2D cross-section called quasi two-dimensional test of a wind tunnel testing, this is how you look like. If you look from above, you have a wing which is a constant cross-section like a chocolate bar. This is called Hershey bar wing. It's not my name. Hershey bar, the chocolate bar, okay? This is called chocolate bar wing, right? If you look from above, this is Hershey bar wing, plan form, okay? Usually this is the width of your wind tunnel test section. So whatever the width given, okay, whatever the measurement of your force, like a lift force, drag force, moment, divided by this width gives you per unit span value of your lift and drag and moment. Then you are going to normalize it by dynamic pressure, and the cold length gives you lift and drag moment coefficient of 2D cross-section, right? That's what you're going to find out doing wind tunnel testing, right? CL, CD, CM, typically quarter code, that's what you're going to get. So those kind of things can be determined by running wind tunnel like this. In other words, you're going to create a model, which is a constant cross-section. You're going to extend from left end to right end of your test section, whatever it is. This is the wingspan. So whatever the value divided by wingspan gives you the value per unit span value that is going to create section lift drag moment coefficient. Is that right? Okay. I think we covered that in arrow. Okay. And then front view is, of course, it's like a constant cross-section throughout from left end to right end. This is wingspan B. If you take a look at from the side, it is going to show the unique cross-section. This is called airfoil. So oftentimes you're going to do a wind tunnel testing just to find out cross-section property. That's called airfoil aerodynamics. Okay. Everything is per unit span based. Okay. Obviously, this is the leading edge. This is the trailing edge. Leading edge comes with usually leading edge radius. And if you draw a straight line from leading edge to trailing edge, it's called chord line. Okay? And the length of that is chord length. Of course, you know that. Chord length is C. Right? Okay? And then if the airfoil is symmetric, you don't need any of those. But suppose if you have a camber, you have to specify the camber. Okay. Now, in order to specify the camber, first of all, you have to determine mean camber line, which is in between upper and lower surface at every location. So this is an intermediate location between upper and lower surface. It's called mean camber line. Okay. If you have a camber, mean camber line is not the same as chord line. There's a difference shows up. So maximum difference is called maximum camber. And then location need to be specified. So this is the location of maximum camber, and this is the value. So the difference between mean camber line and the chord line is called camber. So this is the maximum value of that, maximum camber location. Okay. Maximum thickness, if it's a standard NACA airfoil, it's usually quarter chord. Did you know that? Quarter chord is usually maximum thickness location. That's conventional design. Why is that? Why is that? Why people choose quarter chord as a maximum location, maximum thickness location, and then why people call that conventional? Because quarter chord is location of aerodynamic center. That's why. Okay, that's why, and then it usually works fine. Okay, so airplane behaves just like an airplane. If you choose the different location, sometimes it works really good, sometimes it works terrible. Can you give me an example of non-conventional, which is maximum thickness, not the quarter chord type of airfoil? Do you know? Supersonic airfoil, sometimes, yeah, you do that. And also, very famous one, World War II airplane. Let me find out something, okay? I think you've seen this in AE1, but non-conventional cross-section. One above is a conventional cross-section, maximum thickness quota code. I think this is don't twist. I think. Don't twist or devastate, either way. Airplane in the bottom. Where is the location maximum thickness? It's shifted, right? Around here. It's very close to half code location's maximum thickness. What kind of airplane is that? This is P51D. This is natural laminar flow NACA 6 series airfoil. Maximum thickness location is intentionally shifted aft. It's a unique shape. This one is a very successful design, but usually airplane may become horribly bad if you do off-design choice just like this. Okay, this airplane may not necessarily be a nice airplane to ride, but it worked very good. Okay. All right. So those are all AE1 stuff. Any questions so far? So this is airfoil. Okay. Now, obviously, airfoil lift and drag coefficient is defined, obviously, lowercase l, lowercase d, represent this is a lift per unit span. This is a drag per unit span. Everything is per unit span. So this is all 2D cross-section properties. Okay. So if the cross-section is completely symmetric, it behaves just like this. You guys know that. At the zero angle of attack, you're not going to create any lift zero at the zero because it's symmetric. As you increase your angle of attack, you're going to increase the lift coefficient, usually linear manner, until it hits stall point, which is usually the maximum CL. This is called CL max. Okay. Those are the data set you should get firsthand. Whenever you choose your cross-section of a wing, you're going to get those information to begin with. So this is a slope of a lift curve, CL alpha. Have you ever heard of it? This is called lift curve slope. What is the value? This is in AE1, we used A0. But in flight mechanics, we're going to use CL alpha. Meaning is, this is DCL D alpha, that's why. Lift curve slope. What is the value? Typical value? Anybody? What is lift curve slope of a cross section of a wing of an airplane? Anybody know that?
2 pi.
2 pi. Correct. Good for you. What's the unit? 2 pi what? Per radian. Inverse of radian. Do you remember that? If you convert it to per degree, what? 0.11 per degree. Do you remember this? Of course, you know. Lift curve slope. Lift curve slope is fairly independent to any shape cross-section. So just about any airfoil, you remember, it's about 2 pi. If it's very thin, symmetric cross-section, it is 2 pi period. If you're talking about cambered, fairly thick cross-section, it's slightly less than 2 pi per radian, but it's fairly close to it anyway. Okay, so remember that. This is a plot of CD to alpha, which is not very good plot. But anyways, usually this is CD to CL, but this is called drag polar. Drag polar is how much drag coefficient increase is associated with lift coefficient increase, which is super useful information. In other words, this is one of those purposes why you use X-Prior 5 to analyze 2D cross-section. You're going to come up with the drag polar information. That drag polar is going to be a driving factor of your airplane performance. Okay, so first step of using software is to determine drag polar. Okay, your software actually can do a very good job for that over the range of Reynolds number, range of different shape. Okay, you're going to actually run those things to build a database of your cross section. So Your cross section, which is airfoil, the behavior of it is going to be making a basic character of your wing. If you do a poor choice at the very beginning, your airplane sucks no matter what you do later on. Your aerodynamics designer suffers until that person dies, or until that person graduates anyway. Forget about it. I did the poor job, but it's in the past. I got a job at the Boeing, so who cares? But it is true, if you do a poor decision making at the very beginning, your airplane sucks, and then there's not much thing you can fix it. In other words, my airplane is a supersonic airplane, but we decided to go with this super thick cross section. Wait a minute. I mean, no matter what you do, your airplane sucks. It's not supersonic airplane. Okay, so basic characteristics is going to be rock set when you choose the cross section to begin with. So that's why the software is super important. In other words, if you choose a tremendous range of different cross section to begin with, you can do it. You can spend some time, build the database before you actually start doing your wing design. Okay? You can only do it by using software. This is a huge advantage of using software. Okay? Okay. So this is the lift up throw. Here we go. Okay. Like I said, this is about 2 pi per radian. Okay. Now suppose if you put the camber on your cross section, it's called cambered airfoil. You probably want to put the camber, right? And then you really need to think about why we want to put the camber. What is the benefit of camber to begin with? If you put the camber, if you plot the same thing, this is a CO alpha plot, this is a CDC. No, this is CDC. This is drag port. How come the other one is CD over alpha? I don't know why. But what the heck? I mean, this is CD alpha. What the heck?
The other one doesn't look like a
CDC. Well, usually CDC alpha. Well, it's a Air Force Academy professor's fault. Or the textbook. I have no idea why. I mean, okay. Anyways, usually you usually plot in CDCL. It's a drag polar. So if you put the camber, what happens is you're going to, of course, slightly increase peak value. That's one thing you can notice. CL max is slightly increased typically, and also home curve is shifted to the left. Now, at the zero angle of attack, you are going to actually create the rift coefficient. In order to have a zero rift, you are going to pitch down, right? You're going to pitch down to have a zero lift. This is called alpha zero lift. Zero lift angle of attack. Zero lift AOA, angle of attack. Okay, so you are going to start showing zero lift angle of attack for cambered airfoil. It's always slightly negative angle of attack. In other words, you have to pitch down this much to have a zero lift. Because of the cambered airfoil, you are already producing lift at the zero angle of attack. Okay, so obviously, when you attach your wing to your fuselage, you have to think twice. Okay, if you use a symmetric wing, of course, this is attachment angle. But if your wing is already have a camber, attachment angle is going to be probably slightly shifted to the negative angle. Otherwise, it's not very good. So you have to think twice about that. But what is the great benefit of it? Great benefit is this one, of course. You need to clearly see the great benefit. In other words, in order to increase the lift, drag penalty is minimized. That's what the cambered airfoil really is. If it's a symmetric airfoil, if you want to increase the lift, drag increase is always associated as a penalty. Now, you can avoid such a penalty or minimize the impact if you put cambered airfoil. That's a great benefit, obviously, you can see. Okay. However, CDCL plot, if it's a symmetric wing, minimum value is right here, right? So this is a drag minimum value, CD min. CD min is shifted. CD min is always shifted if it's cambered. Okay. So the drag polar characteristics is going to be slightly modified if you put the camber. Okay, but still you probably want to put the camber, especially for low speed airplanes. Okay. Now, so that's the effects of camber. Okay, next one is the effects of Reynolds number. Suppose with the same cross section, if the Reynolds number is increased, of course, it's going to be very favorable in terms of producing lift. CL max value bumps up. In other words, if airplane flies faster, which is usually good for aerodynamically speaking. In other words, airplanes' most difficult maneuver is flying low speed. Flying low speed is usually not very good for airplane. Okay. This one is a Reynolds number effects for drag polar. Again, higher Reynolds number is better. In other words, drag penalty is going to be minimized as an impact, negative impact. Okay. All right. Next one is a moment coefficient. Moment means pitching moment. Now later on, we are going to take a look at the two different moments, but so far we are going to take a look at lift and drag and pitching moment. Okay. So this is the moment coefficient. Moment coefficient depends on where you take the moment with. So moment coefficient usually comes with subscript. If it's taken at the leading edge, you put the L dot E dot subscript. If you took it like a quarter chord, half chord, you're going to always put the subscript for the moment coefficient and also moment value by itself. Okay. And when you take the moment, of course, you can take moment just about any location along the code, but the common choice is moment taken at the aerodynamic center. Aerodynamic center is usually close to quarter chord. You know that from Aero 1. Okay? The reason here is if you measure the moment at aerodynamic center, it is going to be constant across the wide range of a lift coefficient, as you can see. Okay? Do you guys know aerodynamic center location? Can you find out by using equation? What is the location of aerodynamic center equation? X over by AC is equal to, anybody remember from aero? Eh? Minus what? Something like M0, A0 plus 0.25, something like that. Do you remember that? Okay. What's M0? Well, A0, of course, you know, this is CO alpha. What's that? CM quarter code. D CM quarter code D alpha. Okay, this is the slope of a quarter code moment coefficient. This is the slope of a CL, lift coefficient slope. CL alpha is essentially D CL D alpha. Okay, so you take the ratio between them and add a 0.25. Okay, so suppose, so this is CM quarter code D CM quarter code D alpha. This is the how much change CM quarter code happens with respect to alpha. At the aerodynamic center location, CM quarter code is constant. CM quarter code is constant. What do you mean? CM quarter code is constant. If the CM quarter code is constant, what's this? This is 0. If this is 0, where is the location of aerodynamic center? Quarter code, that's right. That's what it says. Okay? So quarter code is usually the maximum thickness for standard or conventional airfoil 4 and 5-digit series. The reason is that's the location of aerodynamic center. And the airplane behaves relatively good if you use conventional design. Okay? So please remember those things. Or another quiz, I don't know which one do you want. If you don't remember certain concept, I can easily create the quiz to make yourself remember what you learned from Aero. You can do it, right? Can you derive this? Probably. Can you derive this? Probably, yes. It's easy. Okay. So I don't have to do quiz, right? Can you derive this? If your question, I don't know. Well, so let's do a quiz. Can you derive this?
Oh, yes.
Yes, of course. We know that. Well, if so, yeah, we don't have to do a quiz.
Technically, you won't have there.
Eh? Okay. Anyways, it's easy to derive it. Anyways, this is the location of aerodynamic center. Aerodynamic center is quite important for airplane design. Now, each wing, you are going to define aerodynamic center. Now, as an airplane as a whole, you also need to determine aerodynamic center. That's actually not called aerodynamic center. Aerodynamic center of the entire airplane is called neutral point. Neutral point. Okay, that's right. So we are going to cover that later. Okay. How can we determine neutral point? Yes, you can. I'm going to let you determine neutral point of the entire airplane later. Okay. So this is the NACA 2412 airfoil NACA airfoil data chart. Okay. NACA airfoil data chart is actually given here. It's again coming straight from aerodynamics, but if you go back to your course homepage, course materials, you can find the NACA conventional airfoil data here. Okay. You can click here to visit NACA airfoil data. So this one is 2412. So just click here. This is NACA 2412 data chart. Okay. So now you're looking at the NACA 2412 data chart. So this is a plot of multiple things. Remember this. So this is a two data set. This is one of those data sets. This is the plot of a section lift coefficient plotted against angle of attack. This is called CO alpha plot. Okay. Of course, you can read off lots of different value of Reynolds number. Reynolds number plot is 3.1 times 10 to 6 all the way to almost 9 times 10 to 6 Reynolds number. Multiple data plots. Okay. This one is a different type of data set. This is a moment coefficient at the quarter code moment coefficient plotted against alpha. Use this scale for that data set. This data set use the rest of the scale. About half of the class make this same common mistake. Picking up a data value here using this scale. No. Two different scales. One scale for moment coefficient, which is this set. The other thing is lift coefficient scale. Okay. Right hand side is, of course, two different kind of plots. One is drag polar. So those are the drag polar plots. So this is a plot of lift coefficient against drag coefficient. One of them is completely different data set. Why is that? This thing. Anybody? This data, this set of data belongs to the flap. Is this a flap? No, it's not flap. It's a different roughness. Sorry for that. So one of the data set is a Reynolds number 5.7 times 10 to 6, but the standard roughness, you are going to simulate the rough surface. And then this is the increase of drag coefficient due to the rough surface. Okay. The rest of them is smooth surface. And this plot is moment coefficient measured at aerodynamic center plotted against lift coefficient. Here we go. So the definition of aerodynamic center is the moment coefficient becomes constant. So that's why it's flat. And then by plotting this, each one of those data sets actually determines the AC position. Aerodynamic center position is actually determined at the X and Y locations. Okay. Of course, you know those things, do you? This is just 100% review from fluid mechanics. I mean aerodynamics. Sorry. Okay, so you know that. And then tremendous amount of data sets available if you want to take a look at those things. Okay. This is the original report. NACA report 824. This is how many pages? I don't know, 800 some, I don't know how many pages. You can actually download it. It takes some time to download. It's a huge amount of data set. Okay. So this is a whole entire series of NACA report 824. How many pages? I don't know. About 400 pages? Looks like. Yeah. So this report actually contains entire sets of data. Okay. So lots of different sets of data. Okay. So if you want to download it, you can download it. Okay. All right. Any question here? So this is a standard NACA 4-digit, 5-digit designation. Usually we are going to stick with NACA 4-digit. First one digit describing maximum camber in % of the code. Second is a 1 digit describing the distance to the maximum camber location measured from the leading edge in 10% in code. Last 2 digit is maximum thickness of the airfoil in % code. So pop quiz, what does NACA 0012 mean? What kind of airfoil? Symmetrical, 12% maximum thickness, location is quarter code, maximum thickness. Okay, that's right. Okay, so this is going to show up on exam. Of course, you can easily solve it. So next page.
I like that.
You write that, yeah. So let's take a look at example A21, page 7. A NACA 2412 airfoil with a 2-meter code and 5-meter wingspan is being tested in a subsonic raw speed wind tunnel at standard sea level atmospheric condition with a test section velocity magnitude 42 meters per second at angle of attack 8 degrees. Okay. What is the airfoil's maximum thickness, maximum camber, location of maximum camber, and zero lift angle of attack? Also, how much lift, drag, pitching moment about its aerodynamic center is the airfoil generating? Okay, interestingly, first question is, okay, so what is the first question? What is the airfoil's maximum thickness? 2%, 2%, right? 2% of 2-meter code. What is it? 12? No?
12%.
No, that's a 2%.
You said maximum thickness?
Maximum. What's the question? What's the question? First, the question is.
You said maximum thickness.
Yeah, you said.
Maximum thickness. Yeah, that's right. 12%.
Oh my goodness.
Oh my goodness. 12% of the 2-meter code. What's that? 0.24 meter. Right? So maximum thickness. Okay. What is that? Maximum camber. 2%. 2% of 2-meter code, which is 0.04 meter. This is the maximum camber. And the location of maximum camber, it's a 0.4 C of 2-meter code. So this is a 40% code, which is 0.8 meter. So this is the location measured from leading edge of maximum camber, right? Oh, that's easy. So this is a standard 4-digit NACA. Next thing is, let's find out the Reynolds number of test condition. Reynolds number is rho BC, code length C, divided by mu. Standard sea level density, 1.225 kilogram per cubic meters. Velocity magnitude given 42 meters per second. Code length 2 meter. Viscosity is 0.0001789. Okay, 5 more minutes. Kilogram per meter sec. If you compute Reynolds number is 5,751,817, 5 million, 5 times 10 to 6. Okay? So obviously you're going to choose a particular data set out of this. Yeah. So you're going to basically pick up, okay, well, this is the closest possible data set square. Okay? So you're going to follow through. This is 5 times 10 to 6 Reynolds number data. Okay. So under this Reynolds number, okay, alpha zero lift, what is it? Anybody?
-2.
-2, yeah, okay, I'll take that. And if alpha equal to 8 degrees, you can get the lift coefficient CL what's 8 degrees? If it's 8 degrees, right here, 1 point, not quite 1.1, 1.05.
Yeah.
Okay. Not quite 1.1. Okay, good. So CL I got 1.05. Okay. And then next thing is, if the CL is 1.05, you're going to take a look at the drag polar plot by yourself. What is the CD corresponding to it? I got 0.0098, something like that. And CMAC, I got about negative 0.05. Please make sure you read off the same value. Okay. Now, if you compute the dynamic pressure Q is 0.5 rho v squared. So this is 0.5 times 1.225 kilogram per cubic meter, 42 meter per second. This thing square, it's about 1,080 Newton per meter square. So this is dynamic pressure. Front-form area S is equal to span times chord length. This is 5 meter times 2 meter. So this is wing area 10 meter square. So how much lift per unit span do you have? The CL times Q times S. If you plug in those values, you get about 11,340 Newton. This is per unit span. Well, not the per unit span, this is the period. Force, yeah, that's right. This is the lift force, drag, CD, Q, S. If you plug in the value, you get 105.8 Newton. What is the moment at the aerodynamic center? This is CMAC Q S times C. So this is going to be negative 1,080 Newton meter. So those are the values. Those are the values you can get out of this test: lift force, drag force, moment value measured at aerodynamic center. Here we go. It's a very simple practice here, so please take a look at it by yourself, okay? So let's stop here today. Any question? Next class, we're going to pick up from page 8 of Unit A2. We're going to continue on NACA airfoil data chart, okay? All right, see you guys back on Saturday. Start working as a team.
You can.